Hello, welcome to AC circuit analysis. We have kind of a more complicated problem here, but once you break it down, it's not going to be too bad. So what we have is a circuit. We have a unknown voltage source, we call it Vs here. There's some current coming out of that, and it's going through some line impedance here, which is resistive and inductive. But then we have three unknown loads here, load 1, load 2, and load 3, and we have the current flowing through each of these loads labeled as I1, I2, and I3. But importantly, we also know the voltage from here to here, kind of across all of the loads which are in parallel. We know that voltage to be 250 angle of 0, and this is an RMS voltage. So we're given a bunch of additional information. Load 1, this guy, absorbs an average power of 8 kilowatts with a lagging power factor of 0.8. Remember, I told you these words lagging and leading are really important. Load 2 absorbs 20 kVA, so that's a little different than the real power. This is telling us it's telling us the complex power, or the apparent power, the magnitude of the complex power. But it's also telling us the leading power factor of 0.6. All right, so we don't know what these loads are, but it gives us a lot of information about how much power it's absorbing and something about the power factor. Load 3, it just gives us the straight impedance, 2.5 plus J 5.0 ohms. So we actually know what this impedance is. Now the question doesn't really ask us anything about these loads. It asks us, if the frequency is 60 hertz, what is V sub S as a function of time in the steady state? Which is basically this voltage source out here, which we really didn't draw, but we know there's a voltage source there. And we're asking, we don't even want to know the phasor value, we want to know the steady state value of it. So we have to think logically about this, okay? Even if you don't see the final destination of where you're going. They give you some information about load 3, they give you some information about load 2, they give you some information about load 1. So from all of this, we should be able to reconstruct enough information in order to figure out what this voltage is, what this phasor voltage is here on the front end. And then from that, of course, we can then write the steady state value down. So my advice is, if you don't really know, like when you're solving a problem like this, you don't yet really know what the exact path to get to where you want to go. But what you do know is, for instance, they give you the load impedance on L3 here. That's given to me. So I know what this is. And I know what this voltage is here, which this is a direct parallel connection. There's nothing in the way. So if this 250 at an angle of 0 is across load 1, it's also across load 2, it's also across load 3. So before I can do anything else, I know that I can figure out what this current is, I sub 3 is. Because I know the voltage across it, and I know the impedance that's given to me in the problem. So I can calculate I3. So my thought process here is, even if I'm not quite sure I know how to do it, I'm going to try to calculate I3, I'm going to try to calculate I2, I'm going to try to calculate I1. That, when I add them all together, is going to let me calculate I sub S, and then I'll go backwards and figure out what V sub S is. So that's my overall strategy. So let's just go off to the side here and see if we can figure out how to calculate what this actual current I sub 3 is. I sub 3 is just from Ohm's law in the phasor domain, is voltage divided by impedance, right? So the voltage we already know is 250 at an angle of 0, and we're going to remember that this is an RMS value. We'll write it down in our units. And the impedance is 2.5 plus J 5.0. So on the top we have our phasor as a polar number, on the bottom we have it represented as rectangular. That's okay, just stick them in your calculator, and what you're going to get is that I sub 3 is 44.72 at an angle of negative 63.44 degrees. And the units here